Hey guys, what is going on? Welcome back to another AI coding tutorial. Today, we are going to be doing some deep Q learning neural networks. Now, what does that mean exactly? Well, if you've never heard of this term before, you don't know what I'm talking about, I just published an article where I explain exactly what deep Q learning is, how it works, and what really is the thinking and logic behind it. So if you're not sure, go check out that article. It's in one of these corners up here. But otherwise, if you're confident in DQN and your knowledge of deep Q learning, then you've come to the right place. We're going to be going over the coding implementation to create a deep Q learning network. And we're going to be going over every single line of code so you really understand exactly what we need to do. All right, so in order to do our deep Q learning implementation, we're going to be using the OpenAI Gym library. Now, this is a library full of games that OpenAI, the company, has made that we can use as kind of a practice training ground for our program. So we're going to be using the CartPole environment, and we're going to be training an agent that can play this game correctly. So what is the CartPole environment? To answer that, we're at OpenAI Gym's website. And here we are at the CartPole V1 environment. And this is the game that we are going to be trying to solve. This is the game that we're going to be trying to create an agent which can beat. And as you can see, there is a cart and a pole, and the AI will try to balance the pole on the cart by moving the cart back and forth, left and right. And at first it'll be pretty bad at it, but it'll train, it'll get better, and eventually our goal is to be able to make it balance the stick for at least 2 seconds each try. All right, so we're here in the Anaconda Navigator. Now, we're going to be using Python as our coding language, and we're going to be using PyTorch as our machine learning framework in order to do this. So I'm going to be using the Jupyter Notebook to code, but you can use whatever you want as long as it supports Python and PyTorch. If you want to know how to download Jupyter Notebook, look up a tutorial. There's many of them, I'm sure. But we're just going to jump right into it and start coding. All right, so we are here in our Jupyter Notebook, and we're going to start coding. First thing we need, of course, is to just put in our imports. So I'll just get those typed up really quickly. All right, and there we have our imports. These are all the imports that we're going to need for PyTorch and using that deep learning framework. Here we have the, we're importing the gym library. We're doing math, random, numpy, all these different ones. And then here we just have some housekeeping imports. But there you have it. So we can run that. All right, so after our imports, the next thing we need to do is just set up our environment. So we're going to be playing on the CartPole game, if you remember. So I'm just going to say environment equals gym.make CartPole -v1 because we're doing version 1. So here we go. Oh, I'm sorry. The P is capital. I remember, see, we all run into little bugs like this and that. All right, so now that we have our environment, let's just see what are a few things that we can do. So we can use env as kind of the keyword when we're handling any actions having to do with our environment. So I'm going to say environment. I'm going to reset the environment, and I'm going to say environment.step, and this is how we make an action. So remember, we can go either left or right. 0 would mean go left, or 1 would mean go right. But regardless, these are the different actions you can do. So if I ran this, it would create an action. Now, we want to get information from the environment every single time we take an action, right? So the different things that we can get from this, we can get the state, the reward, and the done. So I'm going to leave this blank for the next part. So every time we take a step, this is the information we get. We get the state, we get the reward, which is the appraisal of our action, and done just says, did we complete the game? Which means, did we, like, quote unquote win, or did we like die and fail? And if so, does the game have to restart? So you might be wondering, okay, well, what does this do? Let's just say print state. And let's see what we get. So I'm going to run this. And as you can see, we have 4 different numbers in the list. Now, these numbers represent kind of the coordinates of the pole. So this is the information that these 4 numbers is the information that we're going to be using to decide what our next action is. So we're going to be creating a neural network, right, which takes in these numbers and prints out an action. So now let's see what the reward is. I run this again. It's 1.0. Now it's 1.0 because we didn't die on the first move, obviously, off of the first time step. And every single time you survive one more round, it's going to say 1.0. It's going to give you a reward of 1. Finally, I'll say done. And this is false, right? We haven't finished the game yet. But we could say in the actual game, we're going to use the done to reset the environment once the game has finished. So that's kind of just some housekeeping ones to see how the environment works. Just gonna put me right here. Okay, so now we're gonna do the first step of creating our AI, and that is, of course, creating the neural network. So we need the neural network to take in the state, which is the numbers that we saw in the previous clip, and it needs to output the Q value of the 2 actions it has available. Right, so we need to, at first, obviously, it's going to be random guesses, but the hope is that it will be smart and it will know when it sees the numbers that are the state, it'll know how much value it is to go left or how much value it is to go right. So first thing is first, we're going to create the class. The neural network is going to be a class, and it's going to inherit some attributes from the nn.module, one of the imports that we did here. And this is just going to be some of the functions and things that come along with a neural network. So instead of needing to code that all out ourselves, we can just grab it from PyTorch. So I'll show you what that all means in a second. We're just helping it inherit right now. So we're going to say super init. We can inherit. And now we're going to create the different layers to a neural network. And if you're not sure what the layers of a neural network means or what even a neural network is, check out the article up here or on one of my sides that goes over what a neural network is and how it works. But we're going to create a very, very simple neural network. So we're going to say nn.sequential. And what this just means is it's going to have multiple layers, and it's just going to take the output of the first layer and bring it to the input of the second layer. So it's just going to go through each layer sequentially. So the reason we're able to do all this is because, of course, we inherited the attributes from the larger class, the nn.module. So the first layer is going to be a linear layer. Basically, it's going to have 4 inputs, which is, of course, as we talked about here, the state is 4 numbers. So those are 4 numbers entering it. And at the output of this layer, there's going to be 64 numbers. So then we're going to do an activation function on it. So we're going to say tan h. We're going to use tan h as our activation function. And then after that, we're going to do a second layer. And this linear layer, of course, needs to take in 64. And it's going to output 2 because we have 2 actions that we are going to take. So this sequential layer would take the input, the state, which is 4 numbers, turn it into 64 numbers, pass it through the activation function, and then finally the last layer, which would output the Q values for each of the actions. So there we have our layers as attributes of this class. Next, we're going to do is create the forward class, and this just says, oh, pass. This is just a method, and it's just going to say, okay, well, we're going to do self.netT, and it just says anytime we call the class and we put input into it, it's just going to take t, the 4 numbers, and it's just going to pass it through that. So it's very simple. And then I'll say return t. Okay, so we're going to set up another method, but we're not going to write it yet. And I'll tell you, and we're going to come back, we're going to write it in a second, and I'll tell you what it is. Basically, this is just going to be pre-processing for our state before we send it through the different layers of the neural network. But we're going to get into that later. So for now, we're just going to say, we're going to run that as it is. And of course, sorry, we need to do a return here. and just say, we'll just say print OK. That's kind of a placeholder for that for now. And run that. Okay. So there we have our neural network. Okay, so the next thing I need to talk to you about is something called Epsilon greedy. And this is just one of the things that we use in deep Q learning, and actually Q learning in general, which decides when we want to switch from exploring the environment to exploiting the environment. What do I mean by that? Well, what I mean is that in the beginning, we want our agent to just basically take random actions and explore and see, well, if I go to the right in this scenario, is that better or worse for me? And just learn more about the game. But then over time, we want it to begin to start exploiting the environment and taking actions with deliberation and with conscious thought behind it. So how we're going to do this is we're going to create a function which creates a number which decays over time. And this is going to be our quote-unquote epsilon value. And as time goes on, it's going to decay. And as it decays, the agent will be more likely to exploit the environment rather than explore the environment. So let me show you how that works. It's going to take in different values, which I'm going to write out really quickly. You have the start value and the end value, the decay rate, and the current step. Okay, so basically, we're going to use 1 for our purposes as a start value and 0.01 or maybe 0.001. And basically the epsilon value is going to start at 1. It's going to decay over time until it hits 0.01. The decay rate is how fast it goes over time. And we need to have the current step because remember, the further along you are, the lower the epsilon value is going to be. So it calculates how large the epsilon value is depending on how far you are through this. So this is just a simple function. I need to indent, which takes the values, and I'm just going to write this out for us. Start minus eps end times exponent of And so basically what this does is it's just going to make the epsilon value decay as this is basically just an exponential decay function, right? So it takes in these values and it says, okay, from 1 or whatever we define this to 0.01, whatever we define this, it's going to decay at an exponential rate. Okay, so a rate of exponential decay to clarify that. So I'm going to run this and it looks like I have I forgot colon. There we go. So I'm just going to show you how this works basically. So let's just say I set t equal to 5 and t would be our current time step. So that means we're very early on and I want to call decay. So I'm going to be like, okay, well, let's say epsilon equals decay. And we're going to say epsilon start is 1. Epsilon end is 0.001. The decay rate, we want it to go down by 0.001 every time. And then finally, our time step would be t. And let's just print eps and see what we get. And as you can tell, it's a very high number. It's very close to 1, which means that at this point, we would be most likely to explore the environment. But let's say it's been a very long time. Let's say it's been 500 time steps. Then the number decays over time. Now it's at 0.60. If we made this larger, like 2000, at 2000 time steps, now you're much more likely to exploit the environment rather than explore the environment. And the way this can be used is, let's say we're at T2000, we can just do a simple if statement, which is we can say if a random, I'm going to do pseudocode here, if random number is less than epsilon, if it's less than it, then we explore the environment. Else we exploit. So this is just pseudocode, but you can imagine as it decays over time, we're more likely to exploit the environment because a random number between 0 and 1 would be greater than epsilon, whereas in the beginning, a random number between 0 and 1 would be less than epsilon. So that is how we end up using it. All right, so we are making good progress here. And the next thing we're going to do is we're just going to initialize all the values that we need. So first thing we're going to do is create an eps count, and we're going to set it to equal to 0. And this is going to be the epsilon number. It's basically the time set number. As it increases, epsilon will decay over time. But we're just going to use it for other functions as well, because this will be a handy counter of, okay, how many time steps has it been overall in the entire training process? Next thing we're going to do is create the batch size. And the batch size just tells is going to be how big the batches we're going to pass to the neural network for the training stage of the neural network. When we're giving it different states for it to train on, we're going to be like, okay, how big is the batch size going to be? We're just going to make it 32. Next thing we're going to do is calculate gamma. This is part of the Bellman equation, and if you're not sure what the Bellman equation is, check out the article I wrote on deep Q learning, or you can check out the one I wrote on Q learning. It's a fundamental part of both of those articles, and explains how we give a discount to rewards which are farther ahead in time. So we care, the gamma will basically be a discount to values that we calculate far out in advance, because we want to focus more on immediate rewards. So that's kind of the brief one-liner explanation of it, but if you want to learn more about it, check out my article. Okay, so these are kind of the initial values we need to set up. Now we're just going to create the instances of the neural network class. We're going to create 2 neural networks, because in deep Q learning, we use 2 neural networks, not 1. We use 1 neural network to calculate the first guess of the Q value, and we use the second Q network. We use the second neural network to calculate the optimal Q value. So we're using almost 1 neural network to train the other neural network. It's pretty cool. So we're just going to create instances of this, and we want these neural networks to be identical to one another. So we're going to take the target network, and we're going to make all of its weights the exact same thing as the online network. So load state dict, and we want to do the online net state dict. So here we have now created 2 neural networks which are identical. And then we just want to create our epsilon values. So we have a start number, we have a start value of 1, we have an epsilon end value of 0.001, and let's see here. We'll make the decay rate, we'll make the decay rate 0.03. Why not? 0.003. Gosh, I am missing keys right now. Okay. And next thing we're going to do is we're just going to track how long each episode is. And remember, each episode is how long the AI manages to keep the cart up in the air before it falls. Each time it falls, a new episode begins. So this just helps us see how good is our AI actually doing, because we want the episode duration to be as long as possible. That means it's keeping it up in the air for a long time. The last thing we're going to do is we're going to define the optimizer for our neural network. And we're going to use the Atom optimizer, and we're going to be training on the online net parameters, and we're going to set the learning value to 5e to the -4th. Okay, so the optimizer is just part of the training process of the neural networks. If you're not sure what an optimizer is, I believe it's in my article about neural networks. Otherwise, look it up. Not too complicated. So we're going to run this block of code, and there we have the initialization. All right, so that was the end of part 1 of this coding tutorial series. The series is broken up into 4 parts where we go through the entire process of coding a deep Q learning network. If you want to see the rest, it should be uploaded pretty soon, if not out already. So go ahead and check that out.